So first, the rise of the large language models and the cost, right? So we know like the LLM is growing larger and larger. So this basically like each circle over here kind of corresponds to the size of the LLM. Even some LLM like the closed source, for example, the GPT-4 and Gemini, like this closed source LLM, like even the size is unknown, but the rumor is that it's over 1 trillion parameters. And then with the increasing size of the models comes with the increasing cost to train and to run inference on these large models. For example, on the GPT-4, so this is like 100 million estimated costs to train the GPT-4, and Gemini like is even higher cost than GPT-4. So this is kind of the estimates of the training cost. So why do we focus on the inference optimization, right? So it has to be kind of come backward from the application of that. So this is like a projected market size of inference cost versus the training cost. Due to the training of LLM is not that frequent, right? So it's usually just like a one-time pre-training or fine-tuning. And then you may retrain the LLM, say monthly, or maybe just twice or once per year, given the new examples or new data that you collected from users. So the training is actually update is quite infrequent, while the LLM inference is far more frequent to serve millions or even at billion scales of users with a low latency. So this is the cost, like expected market share to train to run the inference of the LLM. So the training cost is just about like 15% of all the cost related to LLM, and the full rest is the inference cost. So inference optimization is essential to meet the criteria of latency. This will affect the user experience a lot, right? I don't think we want to talk to a chatbot that take a long time to respond to you. And also in terms of the energy cost. And we know like right now, is saying like the bottleneck for the LLM maybe is the bottleneck for the electricity it consumes, right? So if there's a way we can optimize the training and inference, especially inference, then we can reduce the kind of the energy bill and become more eco-friendly. For example, the GPT-3 is like a 135 billion parameters, and we can with optimization can reduce the inference from a few seconds to just a millisecond, so that they can serve the ChatGPT better. So this is why. And then in order to understand how we may want to optimize the inference, we may want to look back to how we actually calculate, like what calculations are happening during the inference time. And then that leads back to the attention mechanism, right? So all the LLM are transformer based, and all the transformer based are basic calculations, the attention calculations. So this is like a kind of the recall of review of the self-attention mechanisms. And basically the self-attention, what it does is to capture the relationship of a sequence, say a sequence of length L. So each is a token. So you have L tokens. And then the attention procedure for each of the input token, you need to compute the query, key, and value, right? So it's just a linear projection of the input tokens. And you can just multiply the input token representation or embedding with a matrix of like the query matrix, key matrix, and value matrix. And then for each of the token, you get query, key, and values over there. And you need to compute the attention scores. So the attention score is nothing but you say this is your current token of focus. Then you need to calculate, use the query, right? And then multiply it with each of the queries or the keys over here. So basically it's like this query, you multiply with the keys of the previous tokens. And if it's bidirectional, you can also multiply it with the keys from the next token, etc. Right? So this kind of the inner product of it kind of tells the similarity of it. And then you get the weight. Using the weight, you can calculate the attention weight from that by the query key multiplication. The last step is you need to calculate the final attention scores, which is a weighted sum of the values, right? So for each of these values, and then you use the attention weights, and then you do a weighted sum of that. And of course, you see these attention weights. These are all softmax. So that all the attention weights kind of sum up to 1. And then this is like you just do a kind of a new value from the weighted sum of all the values in the sequence. Okay, so this is the key calculation steps. So basically you have like a multiple copies of matrices over here, right? You remember these matrices, query matrices, key matrices, value matrices. You need to do the matrix multiplication. You need to do the softmax, and then you need to do another matrix multiplication. So that's the calculation in the attention. And then people like in the transformer, there's another one is the multi-hat. So basically, instead of one copy of keys, value, and queries matrices, you can have multiple hats, multiple copies of this matrices, and each basically like you have like this is the ith copy of query key and value. So you have different copies of projection matrices, and then you can just concatenate all the attention scores and do another projection. That is your final multi-hat representations. So this multi-hats, instead of single hats, allows you to capture distinct patterns with each individual copy of these matrices within the sequence. So right now, you know, like all the matrices calculations, and now you also know like in the transformer tension, like we have multiple copies of these query and values. And how can we reduce the storage, and how can we increase the calculations are all kind of based on how we are going to manage these matrices. So on the inference computation, so we will mainly focus on the decoder only inference, right? So basically it's just and it has 2 stages. So the inference task is like given the input sequence, use the LLMs to generate the next tokens, right? So this is basically the input sequence is kind of your prompt to the LLM, and then the next and continued generated tokens are the responses from the LLM, from the decoder model. And in this inference stage, it has 2 stages. The first stage is prefill stage. Prefill stage is just to generate the first token. So it's very like you can just how to distinguish these 2 stages. Just say the prefill stage is the stage you generate the first next token from the LM. It's kind of like the cold start, right? So you need to kind of generate the first token, and then the decoding stage is the following tokens after you generate the first. I think you all have the experience when you use any LLM, even including ChatGPT, right? Usually the first token, it takes the longest time to generate. And then once the first token comes out, the following ones are much faster, right? I think it's an experience that you have.
I found the word decoding stage confusing because I kept thinking, to me, decoding would be getting the response from the LLM back to English, but I wasn't clear what the decoding in this case.
Decoding, so all the decoding of any generative model is a sequential generated autoregressive generation, right? So each time you get the previous generated token as the input to the LLM, and then it will generate the next token over there. Decoding basically just means sequentially generating the token one by one from that. Yeah. So this is in the pre-fill stage. So we just do one forward pass on the X and save the key and the value pairs. So all the keys and values needs to be calculated since it's the first run. So you need to calculate all the keys and values for each of the tokens, and then it can be stored for the decoding stage. That's why the first token takes the longest time to generate, because all the keys and values needs to be calculated from scratch. And then when it comes to the decoding stage, you can reuse the previously stored keys and values from the prefill stage. And then you can just focus on the new token to calculate the key values for the new token. And that will be a much faster phase. Basically, you're trading some storage for faster speed. There. So at the decoding stage, what happens is you generate tokens of Y. So basically, it's the output in an auto-regressive manner. So just generated one by one, because each output will becomes the input of the next iteration. So it's like sequentially generated one at a time. You can reuse some of the previous representation, like the KV cache, so the keys and value vectors of the previous tokens can be calculated and stored, so that it does not need to be recalculated all over again. And then it also may use some token sampling method, such as like greedy or beam search, to figure out, okay, what is the best token to choose from based on the probability scores of likelihood of the word on the token next. So the KV cache is like a very important technique to speed up the decoding phase. It's essential to reduce the compute complexity with the increase of storage. So basically, it's trace of the storage with the compute, and it reduces the computing complexity from quadratic to linear. So this is what it looks like. Like without the KV cache, say you don't store any key values at all from that, then you need to. So basically, then it means that you need to recalculate the queries for each of the previous tokens. You need to recalculate all the keys. So this one needs to be recalculated every time, right? And then and also the values of these tokens. So all of this needs to be recalculated for each of the tokens that is decoded. With KV cache, this is what is stored. So the purple ones are stored because these are actually fixed values there, right? Because remember, each key token, each value token is just the matrix multiplications of the token representation with that key matrices or value matrices. So this actually stays the same every time. So that's why like we can just compute it once and just store them, so that it does not get recalculated. And then we can just focus on the current token in focus, which is token 4, right? So this green one will be calculated, just focus on token 4 and get this new, and also value is to be calculated for this new token. And then we will get only the attention scores for the new token. So this is like greatly reduce the computation speed. But at the same time, it caused the issue of the memories. So basically, it's like inference with KV cache consumes more memories, right? For example, for the NAMA 27B, with the 2K context length as input, it's like it consumes about 1 gigabytes. 8K is like 8 gigabytes, and if you run a batch, it's even larger than the model parameters. So yeah, basically it's like a trade-off between computational complexity and the memory usage. So that is about I think some of the basic background information about the attention, some basic concepts about KV cache is already like a very widely adopted approach to reduce inference time for the decoding stage. And we know kind of the prefill stage to generate the first token, and then the second stage of the decoding stage to generate the subsequent tokens, right? And then let's look at the big picture. There are many, many, many more ways, and actually it's many more than what I thought to optimize inference. And I really like this saying, it's like what gets measured gets improved. So in order to do any optimization, we need to know like what are the metrics that we want to optimize. Okay, so in terms of the performance matrices, because we have two stage, right? And then we are going to have latency measurement for each stage. So we will have prefill latency, which is the time to first token latency. It's like you prompt the ChatGPT and what is the latency you receive your first token response from the LLM. So that is your time to first token latency. And this is a critical waiting time. And the real-time chatbot response to users, right? And it's like a model size, like input length, etc. The hardware you use, GPU version you use will affect this. And then at the decoding, so this part, prefill latency, I think the faster the better. The faster you get your first token response, the better. And then the decoding stage is how many tokens you generated per second. So this is like an inter-token latency. Like, so say after you generate your first token, you will get the second and the third. Then what is the time interval between your second and third token, or the first and second token, right? So this is inter-token latency. It is important and a real-time interaction, but faster maybe not always desirable because human cannot read more than 6 words per second. So yeah, maybe like a six tokens per second is already sufficient for the real-time use cases. And affecting factors for like a batch size and hardware config. I think hardware is everywhere. There. And so that is the per stage measurement. We can also measure the end-to-end latency. So it's like full end-to-end, like covering two stages. The latency to complete the inference process, like the time you prompt the LLM till the time you receive the full response from the LLM. And it's crucial to accessing the overall user experience, right? And there's lots more affecting factors in terms of if you deploying that as a service, that will affect the like network latency as well, like the if you deploy that as a service, and like total tokens to generate depending on your what is the length of your prompt and what is the length of the solution you expect. So that is will also like affect the end-to-end time spent there. And if it's like a service, then we may also care about the maximum request rate. This is how many queries you can support per second. I think that this is like common for any web services you have, right? And using this, I think we know we can calculate like how many GPUs we need in order to get to this QPS. For example, if like only 20 QPS can be served with one GPU, and if you want to reach 300, like minimum, like 300 per queries per second, then you need 15 GPUs to support this QPS. So that will require the hardware resources and also like the network load balancing of the service. Yeah. Okay, so that's the metric. The full space of inference optimization. Yeah, so we have talked about the metrics. We have talked about like different stages of inference. And with these matrices, we want to optimize the prefill, decoding, and the full LLM actually, in terms of the model architectures, like the architecture series I have talked about in our previous talks. I think some of those architectures will help with the inference to speed up the inference. System optimization. So this is more like lower level implementations of how you are going to batch your queries, like batching, scheduling. I think this is more related to how you manage the parallel works implementations of the inference. And then the model compression, I think we have heard about the quantization distillation, right? So how can we get a smaller model size? And of course, that will increase your inference speed. And last is algorithm optimization, etc. So yeah, so this is kind of the full world of where people kind of are researching on and develop these techniques. And in today's session, I will mainly focus on the model architecture and this efficient computation. And then for the rest, like model compression part, I will leave it to the second one, probably in 2 weeks. So on the model architecture, so we want to scale up the model parameters to say to 70 plus B, right? And we may face many like memory issues and compute issues. For example, if it's a half precision Llama 2, 70B, so half precision is just 2 bytes, like 16 bits, 2 bytes, and that leads to you need to like multiple GPUs to load the like multiply by 2, so it's like 140 gigabytes weights. There's like quadratic computational, this is computational complexity during prefill, and L is your context length, like the context window. D is the dimension of the representations. So our motivation is how can we have more efficient transformer architectures? You see the matrices are the main key, right? Can we reduce these matrices, computations and memories? And can we reduce the projection computation, like reduce the computations needed for the inference? And that leads to first the group query attention for the first one, and also mixture of experts for the second one. So this one, I think group query attention, I have also talked about it in the Llama series. So feel free to check my channel for the previous meetups when I talk about group query attentions and also mixture of experts. I think it's in the next meetup about the mixture of experts model. But I will also briefly talk about this so that you get the key idea over here. So the group query attention is mainly for the multi-headed attention. So remember that the multi-headed attention, you have like a multiple copies of query key and value for each of the head, right? Say if you have 16 heads, then it means that you have 16 set of these 3 matrices for each head. And then the multi-query attention is like instead of like, so say assume like you, okay, over here is like 8, say like we have 8. Like normally we will have like 8 copies of these 3 matrices, right? Like distinct, like a different matrices in each of the head. And there's also like a multi-query is like you just, instead of have multi-head, like you just take, for example, a straight average of all the calculated matrices and kind of compress them with the average of these values and keys matrices. But that would hurt the performance, right? So you kind of doing some of the matrix compression. Instead of just doing a straight average of all the heads, you can do group queries. So instead of 8 over here, you can do 4 groups. And then you can just take the nearby 2 and take the average of that. So you kind of doing a a higher resolution than the multi-query over here, and then but a lower resolution comparing to a regional multi-hat, and you still do some compression of the number of matrices you need to store and to calculate. So yeah, so the key idea over here is like these keys and the value matrices can be shared within each group. So for these two queries over here, they are going to share exactly the same copies of value and key matrices over here, so that you reduce your KV cache storage memory requirement, and thus you can further speed up the inference there. So that's group query attention. I think this is yeah, it talks about how we can distribute the KV hash to different devices over here, like Llama 270B. Like it has 16 groups of the heads, and then they are grouped with 8. So each group has 8. And you can have like a 1 KV head per core for this. So yeah, and then the pain point itself is mainly requires less memory of KV cache. Right, so this is like a pre-storing all the keys and values matrices over there. Yeah. So that's the group query attention. The second is how can we reduce the directly the computation operations at the inference stage. So that leads to the mixture of experts model. So the key idea, like instead, like you in your feed forward layer. So this is your kind of decoder, right? So you have attention, you have your feed forward layer. So you replace the mixture of experts layer. You replace this feed forward layer with a mixture of experts layer. And mixture of experts, you can have this individual kind of like individual feed forward network as your experts over here, right? And which is trained and fine-tuned at your training time. But at the inference time, you are only going to use 2 out of 8, right? Based on the attention weights, etc. You're going just to activate 2 out of 8. So instead of calculating the all 8, like doing the forward pass through all 8 sub feed forward layers, you can just do it pass through the 2 network over here. So that will reduce the feed forward calculation costs. You can still scale it up, the number of parameters, but at the same time, you still maintain the computation operations at a fixed number, because no matter how many experts you're going to train, you are always going to use 2. For example, if you set the usage as 2, you are just going to use 2 over here. So the active parameters are fixed at your inference time, even if you scale up the network by adding more experts in your MOE layer. Yeah, so the mixture of experts mainly have like a routing mechanism. So like it's kind of have like a gating network based on the attention scores you have. It's going to have a gating network to decide which 2 out of, for example, out of 8 you are going to activate. So it has a gate network. And also the expert parallelism is effective under distributed setting. It's kind of naturally like each expert can be set on a core or on a small group of devices. Yeah. Okay, I will pause here a little bit to see if you have any questions about this. And for more details, I think you can go to my previous meetup, specifically just focus on mixture 8x7B. And this is basically this is a backbone for that architecture, LLM. Any question?
Well, I'm thinking about the mixture of experts, and I'm trying to figure out how it scores to decide what expert to pass forward, because it selects two.
Yeah, so basically it's kind of like this gating network is going to have, like, say you have your attention scores as your input, and then you are going to have like 8 output, right? And then 8 output is going to grab the top two, grab the top two highest scores, which is acts as your activation for this two. So basically you just grab the highest, the gating network will have 8 output associated with each of the expert. And then you are just going to take the top 2 scores and then do a softmax so that they sum up to 1. And then, yeah, just use do a weighted sum of the output of the corresponding experts there. Moving next, we are going to talk about the optimize the forward computation. So the goal is how can we do the one forward pass as fast as possible. So basically there's a different algorithm like proposed for different stages. Like there's like a flash attention for prefill, like flash decoding. So anything with flash is kind of to speed up the computations for decoding, and also you can run distributed inference. And to understand this, I think I need to change to understand the idea of flash attention. I think we need first to understand the memories of the GPUs. So GPU has many cores, right? And then each of the core, it has like different types of memories in the GPU core. So it has the compute kind of doing all these matrices, multiplication, etc., right? And then there's like a SRAM and HBM. So SRAM is called a static random access memory. HBM is like a high bandwidth memory. So what it feel like from the chart is obvious. Like if your data is in SRAM, it will be very fast. Like because the compute can directly grab the values like very fast, like this 19 terabytes per second. So it's like the compute can access this data like very fast. And if the data is in the HBM, it is much slower than the one in the SRAM. It's like more than 10 times slower, although this is much faster than the CPU RAM. But still, within the GPU itself, it has these two types of RAM. So that leads to how can we best leverage these different memories types so that we can speed up the matrices computations of the attention weights, right? So how can we explore the memory asymmetries over here to get speed up? With I/O is kind of input-output awareness, because every time when you do a compute, it's going to read the data, write the data, etc., right? So how can we distribute the calculations and reduce the read and write, or maybe put the read and write mostly like in the SRAM so that we can improve the overall time to do the calculations, because the calculation is just a small time spent. The majority of the time spent is actually spent in reading and writing the data from the compute to the RAM. Actually, the attention is bottlenecked by the memory reads and writes, just as in like this I/O I/O operations actually takes much more time than the matrix multiplications. So so this is a full kind of processes to how do you calculate the attention output, right? So you have your query key, yeah, it just keeps showing up like query key matrices, doing the matrix multiplications. You may need to do the masking, and then you may do the dropout, and then you need to do a softmax, right? Softmax to normalize all the values. And then you may do the dropouts, and then you do another multiplications with the values to get your final attention scores over here. And this is actually the time spent, say the for on GP2. Like this is how they like measure like how many milliseconds are spent during the full process. And you see the matrix multiplication actually is very tiny. It's like very fast. The majority are on the on the masking, softmax, etc. Because this type of calculation requires more like reading and writing back and forth of the values from the compute to the memories. And what flash attention propose is they reduce the frequencies of read and write there, and by doing the chunking and by like fuse kernel, right? So how can you decompose the matrices so that it's small enough it can be hosted in the kernel, like in that small memory there, and complete all the computations directly on that kernel. And then once all the computation is complete, like all together at complete, and then write it back to to the bigger memories there. So this is what flash attention wants to do. And actually the key idea is just tiling of the matrices, right? It's going to decompose the large softmax. I think they specifically focus on the softmax because there's another paper even I think published like just focus on softmax online calculation. How can you decompose the matrices and doing the softmax on the fly? So that is a paper even published before the flash attention. And flash attention basically takes that softmax online calculations and fit it into the attention framework and implement it on CUDA. And then you got flash attention and you observe like at least like 15% improvements in terms of the inference speed. So if you think about the scale of the LLM and also the energy it consumes, if you are able to save 15% by doing this calculation, it's already saving a lot, right? So yeah, that's why like they think the flash attention is very popular right now. And I think it depends on what GPU. Some GPU like is already welded into the Conda or some like open source framework, like it's already has this CUDA support for the flash attention. Yeah, so the key idea is like decompose it into small matrices. Yeah, so basically you can just do these small matrices calculations on the core and write it back. And then you can just do instead of like writing these values and keys matrices like back and forth, you can just do the calculation at one time in the compute and in that SRAM. And then you just do and then write it back once you get your final results. So load the inputs blocks by blocks. So basically you grab the little block here, you grab another block here, you grab a small block here, you copy it from the outer loop to the SRAM to do all the calculation needed, like end-to-end calculation for the attention, and then you write it back to the HBM. Yeah, that is a key idea of the tiling and exactly how you do the alpha and beta. That requires a long derivation, which I haven't figured like fully out yet, like how they calculate the final alpha and beta over here. But I think yeah, it's I think to understand that, I think it's better to read the original softmax online calculation paper. Basically, this is what it means, right? So in the standard self-attention, you like for each of these like matrix multiplication, softmax, and another matrix multiplication, for each of the calculation, you do the read and write. Like you need to read the matrices, you need to write the results back, you need to read it back again, and then write the output again. So it's kind of like you do this repeating one, right? So you write it and then you read it all over again because just the limited memory is there. So you have to kind of doing like this repeating read and writes in order to do the calculation. So what it does is want to remove this repeated read and write, and then doing all the calculations in the attention kernel with this reduced input and output data transfers between this by tiling, right? So that you can just grab what you need to complete the full calculations all at once in one compute, and do one write back, so that you do not do multiple writes over here. Question? Is there a hand raised? Okay. Okay. That is the key idea. And so yeah, so this is a flash attention, and it specifically focused on the softmax. Like, how can we decompose the matrices and still calculate just by moving from tau to tau, and then we can still recover the original expected values of you do it all at once. So that's a trick hit place. So basically, like, flash attention decomposes the softmax to remove this constraint, and it's actually proposed by a separate paper for the softmax online calculation, so that this one can be computed tau by tau, so that you can reduce the read and write, repeated read and write for the big matrices. Okay, so that is the flash attention, and then there's also like the flash decoding, and as always, decoding has to be with the KV cache, right? Like, this needs to be, like, once calculated, it needs to be cached, stored in the GPU memory. So I think it's in the larger memory there. So it should be cached over there, and then you just focus on the current token, this query vector of current token over there. So this is the same, like, just KV cache idea. And then flash decoding is like they support the parallelisms across the full sequence. Like, they can divide the sequence by chunks. So usually the parallelism is always chunking the data. And how to effectively, like, chunk the sequence and doing the calculation in parallel, and then put it back together and still get the original answer you want. So that's all about the parallelisms over here. So because the queries, remember the queries attention scores, you need to attend to all of the values and keys, right? So you can do this in parallel of just running these queries against, like, this in one, say in one core, this in another core, this in a separate core, so that you can chunk the sequence and then doing all these query T calculations in parallel. So that is like a flash decoding idea. And then on the distributed inference, I think this is more on how you manage the computation across different cores, different GPU nodes, and then the full, like, on different machines. So, and I think it is like for example, you can parallel it according to different heads, right? Like each node can take care of like a one head in parallel. And then this is like a pipeline parallelism, like in terms of the inference on like a very large model. So you may want to distribute it across different nodes. And also you may, based on your advantages of different machines. So some machines can be specifically optimized for prefill, and some machine can be specifically optimized for decoding due to like a different computation properties there. So if you run it on kind of a cloud of machines, you can actually, the cloud can actually smartly distribute the task according to the task characteristics and also the hardware configurations, so that you can utilize the most fit computing resources for the specific task.